hybrid classes. 10 years ago, I had recruited at the New Jersey Teachers Conference, the NGEA or whatever, the one that's always at Atlantic City. And at that time, students were telling me, potential students were telling me, make it online and we'll come. How many of you would like hybrid classes, especially for the evening ones? Well, I guess they're all evening, right? 8:15 is murder. 8:15 at night till 11 is murder. Right. But I like the structure here. I mean, in some ways we're having a hybrid class because unfortunately I have a lot of travel to do with my other side of work. So yeah, I thought that you guys would be interested in it. I'm a little hesitant myself because I depend on eye contact. So I know it might have seemed fine when you guys were doing the online thing, we were at home, but I just absolutely need to see people's eyes. So it bothered me a little bit, but I suppose I would get used to it. Okay. So this one, yes, the Quaternions and the representation. I use the restrictions above to show distinctness. However, some of you use the matrix representation in part 3. First, you proved that the matrices satisfied these restrictions. Was that any better? Did you use that? Was it okay? Well, this wasn't. So, you know, I started with suppose A is equal to A squared. I wanted to show these were distinct. And so you're supposed to show they're not equal. It's basically cancellation law. So if they're equal, then I come up with A is equal to E. But then B would be A, and then A and B won't be distinct. But in the presentation up at the top, it clearly says that A and B are distinct elements that generate the whole space. So I came up with a contradiction of the fact that A and B would have to be distinct. Goran?
No, because I did it completely.
Well, there's more than one way to... I don't know why people say skin a cat. I'm a cat lady, so I don't know if I could...
If we're dealing with defining equations like this, and it gives us that A to the 4th is E, aren't we able to assume that that's the order of A? Right, because why would it give it
right. I use that, yeah, I definitely use that, yeah.
Okay.
So we can take that to mean that 4 is the lowest A to the n.
Well, I guess now I've shown that, you know, if you have to show A cubed as an E first.
Right. Okay.
So A and A squared are distinct, and that tells us that A can't be B, A can't be E, B can't be E, etc. It tells us a lot of things at once. But I just started randomly pulling things apart. And what you realize after a while is you really need an expression for B times A. If you have B times A, you're done. And again, you don't have to go through my calculations. I'm going to post this. It's all feels like PDEs, PDE type calculations, like computing and computing and computing. That's what we did for a large part of PDEs. We just computed. So here, harder ones were, is it true that A squared B is A cubed B? And then it's again computing. We're back to A equals E. And all of them are like this. You can go through and show that they're not equal. And some of you sent me that. And then the second part was to create the Cayley table and from those restrictions. And so you start just putting things together. I don't know how you felt doing this, but I was cursing out the person who assigned the problem after a while because it was very annoying. So I come up with the A inverse is equal to A cubed. I come up with little properties and I box them off once I get them. And I start filling in the Cayley table. So one row and one column is easy. It's the identity. And then I start filling in what these possibilities must be from the presentation. So for example, what's AB star A? Well, I get AB is B inverse A from the presentation. And from that, I'm able to get AB star A is equal to B. One of the things I noticed is you would need some important facts. You would need to fill out the rest of the tables. You would need to know what B inverse is. It'd be nice to know what B inverse is in terms of the AB structure. So once I found that, I boxed it off so that I could use it for my other calculations. But eventually, you get to a point when you're filling in this thing, you're like, I need to know what BA is equal to. Because if I don't know what BA is equal to, I can't fill in any of the parts that have to do with B coming first and A second. And so there were 3 possibilities left. So I used the fact that the Cayley table had to be a Latin square. And so there was only 3 possibilities that I could fill in for b times a. So I used a process of elimination to get what b times a is equal to. And there's not one way to do this. This is just the path I took. B times a, when I tried b times a being certain things, I got contradictions. So using the facts from the presentations. And so I got, for example, I got a cubed is equal to e, and that's where I'm using the order is 4. A cubed can't be e because I already found out the first time a to the power of z was 4. So here I have it. That's a contradiction. So it cannot be the choice, second choice. And then I used number 1, and I ended up with a cubed is equal to a, which is also, it can't happen because we just proved that those things were distinct. So that boxed off that possibility and left me with only one more possibility. Once I had that, it just kind of moved along. So I'm not going to go through the specific calculations. And boy, this would take a lot of board time to put up here. But you get the point. And this table starts filling out. It was scary. It was annoying. It's not one of these things where you can drive from Randolph to Montclair and think about it in the car without getting into an accident. Okay, any questions on that one? What was it like with the matrices? Was it just matrix multiplication and you could see what it was?
It was a lot easier than that method.
Right. I did it in the order that they gave the problem, though. I thought, yeah,
Okay.
yeah. And I thought if I do it the matrix way and then somebody went this way, the other way, and I don't show it this way, they might key my car.
Right.
And I was really annoyed with myself for saying that little Jillian Michaels comment. Because remember I told you I do all the homework you do because it's... All right, number 3. They had these, this was easy. I just punched it on. I'm so lazy when it comes to... This is why I'm a PDE dropout. I don't like doing the computations. I went to Maple and I just cranked them out. And I have a picture for you to see. If you're not a Maple fan, these kind of any kind of computations, having Maple or MATLAB do it should make you a Maple fan. I think Mathematica came out, and I'm going to date myself. Mathematica came out my junior year of college. And I found that there was a piece of software that could do algebra for me, that I wouldn't have to do the row algebra anymore. I was there. I was there. I'm okay with that. Let's see. Okay. This one, I had a lot of questions on this one. I don't know if you can see it. Do I need to blow it up? Can everybody see it? A lot of questions on it. The question was if H and K are subgroups of G and the order of H is equal to the order of K, must it be true that H intersect K is equal to the identity? And the answer is no. I went to the permutation groups immediately because they're known to give you the counterexamples for anything you can just about imagine. So I didn't do this by cranking out all of S4 because S4 is pretty big actually when you crank out all the possible compositions. I just went on the internet and said, looked up for, give me all the subgroups of S4. And I immediately found 2 subgroups of S4 of order 4 that shared some elements other than E. So the intersections are underlined here. So it's not true. But then again, I think some people in the class use does D3 have counterexamples in it? I didn't know if D3 did. D4 does, right? D4, yeah. So some of you use D4, so you found some there. I just immediately went to permutations because I knew that it would generate for me what I needed it to. Huh? What did I don't remember what I put on the first. Yeah, that's what somebody said. I think somebody said D4 gives me a counterexample, so yeah. Well, the condition you would need is H equals k equals prime, that they're a prime number, then you're going to get a intersection that's going to be trivial. So here's how I was thinking. It's not like
I have a quick question. On mine, I used Z8, the cyclic groups of 2 and 6. They intersect at 0, 2, 4, and 6. They're both.
They're identical.
Yeah, they're both order 4.
Right, but they gave you the same subgroup, right? H and K were the same? Because Lagrange's theorem, so here's my thinking, right? You want something, you want to know that you have a real counterexample, that you had something actually different in the intersection. That was, right? So I didn't, right? Obviously, it's the way of thinking. Like, he asked me one question, I'm thinking 10 other questions. Is this true? So yes, of course, you could do that. You could take, but Lagrange's, it's not Lagrange's theorem, but Lagrange's theorem for cyclic groups tells you that you're only going to have one of that particular divisor. Right? You're only going to have one subgroup of that divisor. So you're really taking H and H in that case. So, so immediately my next question would be, what if they, is it possible for them to be completely different, but still share something more than E? It's a natural question, right?
Because it never said anything about distinctness.
Right. You didn't think it? I wonder if it's true. I don't know, those things are like an itch I can't scratch. I have got to figure that out. So I don't know about you, maybe that's just, I start thinking more. So yeah, so the answer to that question is yes, you will get even more if you go up to S4 or something. So the cyclic group theorem tells me that, exactly that, if I take the order of G and look at the divisors of G, then I'm going to have a subgroup of exactly one subgroup of that order for each divisor. So I know that from the cyclic group version of Lagrange's theorem. So that means that if H, the orders are equal in a cyclic group, well, I guess I will find a counterexample if they're, if they're identical to each other, that would be a counterexample. But for the case where they're not identical to each other, I'm going to get the intersection is going to be E, right? Because they're going to be distinct subgroups. D3 also is not good enough. It doesn't give me a counterexample. So I went all the way to S4 and looked up subgroups of S4 to find a counterexample. So I knew that what this told me is, in my search for a counterexample, I can't go to a cyclic group, because cyclic groups are going to either give me that they're identical subgroups, or they're going to give me that, that their intersection is exactly the identity. So I had to go somewhere else. So I went to the first interesting non-cyclic groups I could think of, which is D3, and it doesn't do the job. So I said, oh, I'm not going to mess with D4, I'm just going to go to S4, which is all the permutations of 4 elements. Next, Lagrange tells us that the order of the subgroup must divide the order of the big group. So if H intersect K is it is also a subgroup. It's a subgroup of the big group G, but it's also a subgroup of the mini groups H and K. You can think of it that way, right? So the order of H intersect K must divide the order of H, and it must divide the order of K. So if H and K are equal, I would want the order of that intersection to be 1. That forces me to choose H and K to be prime order, right? Then I'm done. So somebody, Ted, was that you again? Asked me, well, what if they're not equal? What if the H and K don't have equal order?
No,
You're not going to get out of this class alive. Stop giving her questions.
What are you proving? What are you proving?
I'm proving in this one that the conditions, right? What are the conditions I need to put on H and K to guarantee that the intersection of H and K will be the identity, right? So let me shoot that question back at you. Somebody shot it at me, so I'll shoot it back at you. What if the order of H and K, the order of K are not the same? When will that intersection be the identity? That's right. I can just use the same proof, right? So they have to be relatively prime. So you can see that one too. And that's what messed up S4, right? S4 had the order of H, the order of K was 4, and 2 divides 4, And Lagrange's theorem doesn't guarantee you that you're going to have only one subgroup of such a case. So that's why you would, again, go to S4 and to get it to mess up. And in fact, I was already running this proof in my mind, so that told me right away that I'm going to have to actually look for order 4 subgroups of S4. So in Google, I typed, find me the order 4 subgroups of. That's exactly what I did. So I think that this is the clean proof from my scratch work. So there you have the clean statement of the conjecture and the clean proof of the conjecture, Danny.
What?
There's the clean statement of the conjecture and the clean proof of the conjecture.
Oh, okay.
Okay, any other questions on this? Okay, and that was it, right? That was all I got questions on. So, okay, so this is it for spring break. I gave you homework already, and I'm around actually. So it doesn't matter really because I have email and cell phone and everything. So it doesn't matter if I'm around or not, right? Because
Closer to home, is that what you're saying?
yeah.